So, welcome to today's session. Let's wait for a few minutes and then we'll solve problems on band theory of solids. Uh, okay, so let's quickly recap. By and large, what will be taught or what has been delivered in the band theory of solid lectures, week 7. So, let's say I have an isolated atom. So, and with atomic number Z. Okay, and so this is atom's nucleus, suppose, plus Jd is the charge, and there is electron at some distance. Let's say this distance is r. Now, due to this atomic core of uh, positive energy Ze, or let's say this is nucleus just. So the potential energy that the electron will feel at r distance is given by this, right? This is a story of a s- single electron, right? Now, in any solid state systems, what really happens is there are millions of atoms stacked together. So, if we consider these points are just nucleus with positive charge plus Ze, then the potential profile with respect to R will look like this. So, wherever there is an atom, there will be the potential energy of the electron will diverge negatively, because there is just a charge of electron is negative. So from this expression you can see, as r goes to 0, v goes to infinity, but it is negative infinity. Okay, negative infinity. So this is what happens. So this is a charge center, positive charge center, so the potential energy diverges. Again there is a positive charge center, potential energy diverges. Now, when there is an isolated atom, plus Z is the nucleus, and then there is an electron orbiting around that positive nucleus. So there is 1s orbital, and then there is 2s orbital, and so on, right? So this is, then the atomic energy levels are isolated. So let's say this is energy of 1s, then there will be somewhere 2s which will be higher than 1s, right? This is a story of isolated atom. So isolated atom, electrons energy 1s, electron energy, and then 2s. So but then in the solid state system there are millions of atoms, and these are the potential profile. So electrons at this position feels the potential from this atom itself, sorry, this positive nucleus, then this positive nucleus, this positive nucleus, and all the others. Of course the value of the force or the field that is being filled by electrons at here will be less for this and will be greater for this, but there will be some effect. And what this led is that there is a formation of band. So instead of this isolated sharp line of energy, there is a some spread in the energy. So delta E not equal to 0. This was a sharp energy E1s, spin pointed energy. But in the solid state system, the electron's energy will have some bands. So these are allowed region of energy where electron can be there. Then there may be another energy band higher than this one. There is another, and in between this, there is no energy, no allowed energy region. So this is not allowed energy region. Okay, so so. So this has been shown here. This is a energy as a function of distance between atoms. So which we see here is that as we increase the distance between atoms, so these atoms, if we take far apart, then we can treat each of these atoms as isolated atoms, right? Now for isolated atoms, electrons will again be electrons energy will have 1s 2s type of energy levels, which will be very sharp. So these are the sharp energy levels at the very high distance between them. So these are the broad idea of formation of bands. Then what Sir probably solved is that this model of potential we actually approximate by considering very drastic approximation, just the potential well, rectangular potential well. Okay, So there will be potential barrier V, and then there is V equal to 0. Here is some potential, let's say V0. Okay, and this with maybe B or A, whatever we call. So then essentially we'll solve the this is 1D problem. Let's say we'll solve the uh, Schrodinger equation to get the energy as a function of crystal momentum k. Okay, and it turns out that for this model, which we actually called chronic Prenny model, so it turns out that the energy as a function of k is not analytically solvable. So numerically we can find the solution, and again, so usually what we plot is that uh, some function of energy which will eventually come from this solving this equation with some boundary condition. Boundary condition will be like if this is infinite potential well, let's say, then there will be no psi or wave function there. Here psi will be 0 if it is infinite. Okay, then there will be some not equal to 0, like this. Boundary conditions means at the boundary of the potential what is the condition of energy or wave function, etc. So f of E versus energy looks somewhat like this. There will be oscillating function, and let's say this is plus 1 minus 1. Then from the solution we can actually tell, I'm not showing anything, that when f of epsilon lies between minus 1 to 1, okay, then this energy range, so this energy range is allowed. If it is below minus 1 or above minus 1, sorry, plus 1, then not allowed. So same concept here as here what I was saying. So there is allowed region of energy and not allowed region of energy. Okay. So the essence of band theory of solid is we need epsilon of k or E of k energy function as a function of crystal momenta. Crystal momenta k, where p is h bar k. Okay, and this gives lot of information about the material properties, both physical and other properties as well. So for example, effective mass. So effective mass m star, usually we denote it. The formula is given by h bar square by uh, d2 epsilon dk2. Okay, so the idea here is whenever electron is free, so let's say I have a free electron, then its mass is given by me, electronic mass, that we all know, 9.11 into 10 to the power minus 34 SI unit, right? 31 I think, sorry, we need to check. So but whenever the electron roams around in the solid state system where lots of billions of atomic centers are there, nucleus are there, there are other environment, there is some dielectric property of that metal, all these things, whatever affects this energy function, these things makes the mass of actual mass of the electron not to be me but function of crystal momentum. uh, because of energy, as if energy is not constant, but energy is a function of k. So the mass of the electron gets changed, and it becomes a function of k, which is given by this equation. We'll solve some problems based on this equation. And unlike the electronic mass, which is given by this, of course it is positive, the effective mass can be negative. M star is allowed to be negative. It actually not electrons mass, but it actually represents the curvature of energy band. This we can see from this part actually. D2E, dk2. So if this term becomes negative, then effective mass is negative. If it is positive, then if it is positive. Now when it becomes negative and positive depends on the how electronic energy varies with k, right? So let's say yeah. So for simplicity, let's consider this is a sinusoidal wave function. So then effective mass can be uh, at a particular point, let's say up at this point it can be positive. At this point it may diverge as well, right? Because dk equal to 0 at this point. So this can be positive, negative, and again diverge also. Okay, so this was the brief discussion. So let's solve some problems now. So anyone have any question or doubts? Although it was not very, it was totally not detailed. Okay, so let's solve some problem. Okay, so the question is taking origin at the bottom of the conduction band. Let's say I have a conduction band like this. So uh, energy versus k. Calculate the crystal momentum k for a free electron of energy 0.02 eV. Given the effective mass of the electron is zero point 0.2 times electronic mass. So try to solve, then I'll solve. So we need to find the crystal momentum h bar k. So although we call k to be crystal momentum, but actual momentum is h bar k. It is also dimensionally consistent. K is just length inverse. So anyone got the answer? Yeah, let me solve the problem. So it is already said that this is a free electron, right? So for free electron, we know that energy is h bar square k square by 2m. And here given that effective mass m star or m, let's say 0.2 me, and this is also given. This is 0.02 ev, means 1.6 into 10 to the power minus 19. This will be in joule. So h bar k, just multiply these two and take root over of this, which will be around 3.416 into kg meter per second. So this is the crystal momentum. Okay, and there is another important point in this expression actually. So in crystals, so for free electron, energy is this, right? That is fine. H bar square k square by 2m. Now, whenever an electron is within the solid state system, then it is not really free, right? It is feeling so many potential energy, and then electron energy, interaction energy, and so on and so forth. So all these information are effectively put together in this m star. M star effectively takes into that effect of solid state system. Okay, not all the effects, but major effects, especially the band information, that is effectively taken into this M star, as long as it can be represented, the electron can be represented as free electrons energy. Okay, not always we can have this kind of parabolic bands, right? Free electron have these parabolic bands E versus K, E is proportional to K square, but this is not always true. Whenever it can be represented as perfectly parabolic uh, system or perfectly parabolic energy, then only we can bring the information of bands in this M star. Okay. So we need to find the effective mass of electron given that energy as a function of wave vector is this a k square plus b k to the power 4. So again I'm writing the formula for effective mass h bar square by double derivative of energy with respect to k. Okay, so this is the formula we need to apply. So let's try and then I'll solve. That's correct. Option C. Someone raised hand. Uh, no, Pavitra J. No, it's not B. Okay, so let me solve the problem. So let's first find out the derivative of energy with respect to k, right? ddk is a k square plus. So this will be 2ak plus 4bk cube. Then the double derivative. So this will be only 2a plus 4 times 312 b k square. Now we need to find m star at k equal to k0. So h bar square by at k equal to k0. That means, right? So option B is correct. Okay. So third problem. So there is two problem within this a single yeah. So for a solid tight binding approximation, it's given by this. So this will you learn later on. This is advanced topic. So the main point is we have energy as a function of crystal momentum, but this is a 2D system. Okay, that's why there is kx as well as ky, and we need to expand ek around, sorry, k equal to 0, and find the bandwidth of the band. Bandwidth means let's say I have a band like this. This is I'm drawing as a uniform. So suppose this is E2, this is E1, and within this region, this is allowed region, right? So bandwidth delta E is E2 minus E1. Basically E max minus E mean of the band. So first expand this and then find the bandwidth by observing that let's say you'll still get after expanding you'll still get E as a function of k. Then you need to find that what will be E max and what will be E mean. So just take the difference. Okay, so let me solve it. So E is given as E0 minus C cosine of kxa into cosine of kya, right? So E0 and C both are constant. Now cos of x, when x is very small, we can have x square by 2. Similarly, sine of x is nearly x when x is small. So this will be okay 1 minus 2 so E0, and if we multiply this then that will be, so we can ignore this term when kxa and kya are small. Then this will be E0 minus C 1 minus, right? So this will be the lowest order expansion term. Okay. Now the second question requires actually more information. Okay, that way we cannot find the bandwidth of the band. So we need to plot this, and after that we need to find kx or ky, both of these actually, where ek becomes max and ek becomes min. So analytically it cannot be solved unless more information is given. If you have given kx equal to what or ky equal to what, then we could have derived that bandwidth. But now it is not solvable without drawing that band energy versus k. Okay, so I'll skip this problem, but let's find the effective mass of the system as well as density of states. So density of states I covered probably 2 3 lectures before. So from this actually, not this expression. So after we have expanded ek around k equal to 0, then find effective mass and density of states. So effective mass is simple. Now here k is kx square root, right? So basically normal 2D system. This is actually k square, kx square plus ky square. So we'll have d dk is dk of e0 minus c 1 minus a square k square by 2, where I have used k square equal to this, k equal to root of kx square plus ky square. So this will be uh, plus c a square k, because e0 and c are constants. Then d2e dk2 will be c0 square simply. So hence m star is h bar square by c a square. Okay, now we need to find the DOS. So density of state as a function of energy is basically how many number of states are there in the energy interval dE. Okay, that is the density of states. And for 2D systems, we can actually find that L is the, let's say L is the dimension of the system, and then L square by 2 pi square. This is prefactor, always comes in the 2D systems. Then this is 1 by dE dk. This is the formula for density of states when spins are not considered. Spin degeneracy we don't consider here. So dE dk we just found ca square k, so it will be ca square k. So density of states as a function of energy, but we still need to convert it in terms of energy. So energy is simply E equal to E0 minus C 1 minus a square k square by 2. So we just need to find E minus E0 by minus C. So need to find K basically. Okay, so C a square by root over 2 by a square 1 plus E minus E0 by C. So this is density of states as a function of energy. Okay, so fourth problem. Okay, so from the above problem I can give a problem. So let's say given E is the simple form minus C on minus. Okay, so this is the energy as a function of K. Now we need to find the band velocity of electron. What is the band velocity? So for band velocity, or we also call group velocity, the formula is 1 by h bar dE dk.
Sir, I think your voice is breaking, sir.
Okay, okay, so now am I audible better? Hello,
Sir,
am I
now
audible?
hear your voice, sir. But little bit difficult.
Okay, let me rejoin. Okay, Okay, so am I audible now? Sorry, I just got disconnected.
Yes, sir. Yes, sir. Now clear.
Okay, okay. So group velocity just given by this formula, or it is also simultaneously called band gradient velocity. Sorry, band gradient velocity. It is called band gradient because this is just gradient of energy, right? So this just simply directly proportional to gradient or del k of energy. So the problem is solved because we had this dk from the above problem. Now let's move to next problem. So now there will be a three-dimensional dispersion relation. So ek for a 3D system is given like this: beta of cos kxa kya plus cos kza. Again we need to find the effective mass. But at a specific key point, at boundary of first Brillouin zone. So for a 2D system, first Brillouin zone is like this. So this is along kx, this is along ky, and let's say we have a square lattice in 2D. Then these first Brillouin zone are pi by a minus pi by a, again here as well pi by a minus pi by a. Similarly, for 3D system this will be a cube where corners will be pi by a and minus pi by a along kz as well. Okay, so need to find m star at first Brillouin zone points, at the boundary of first Brillouin zone points actually. So here or here or here, whatever. So try to find it out. Kx, ky, kz can be found at pi by a. Okay, Anyone found the answer? Okay, so we need to find m star at kx equal to pi by a. Similarly, ky and kz are also pi by a. So dE dk will be beta derivative of cos kxa. Now notice that here all these things are given in terms of kx, ky and kz, right? And we need to find so when I say dE dk here, this is actually gradient of k. Okay, now gradient of k will be vector, but we are not concerned in the vector part. Okay, so we're only concerned in the scalar part of this problem. So then by dE dk we actually mean corresponding derivative will be done at kx, ky and kz like this. So with respect to kx is given this, and then there will be ky and kz. So again a, now dE dk or d2 e dk2 at kx equal to pi by a, ky is also same, kz is also same, will be minus a square beta cos pi, right? Cos pi plus this is 3a square beta. So m star will be h bar square by 3a square beta. This is the answer. Okay. Okay. So next problem.
Sir, one request is there. Can you please upload earlier this video as I missed it?
Uh, Video means the videos of the earlier sessions, right?
Yes, including this one.
Yeah. So everything is uploaded on YouTube. Uh, okay. So I can provide the YouTube link at the end of the session, and as well as the links for these notes basically.
Okay, sir. Thank you.
Okay, so the next problem is on band gradient velocity again. Okay, so the dispersion relation for phonons. So phonons are just lattice vibration. It also has dispersion in terms of k. So basically, which is given by omega square k. Okay, so omega square k is equivalent. Sorry, is equivalent to what we are giving earlier, energy of as a function of k. Okay, so now we need to find the velocity. Velocity means group velocity that we are just earlier representing an dk. We need to find the velocity at the large wavelength. So k is 2 pi by lambda, right, according to de Broglie. So large wavelength means k is small. Same approximation we used in the previous problem. Using that, we need to find the velocity of phonons at large. Large wavelength means k equal to small. So these are the options. So let's find. So here band gradient velocity will be equivalent to d omega dk, and we are given omega square. Just take the derivative. Okay. So anyone found the answer? If not, then let me solve. So we need to find d omega dk, right? And we are given omega square equal to omega naught square 3 minus cos kx minus cos ky and kz is there. Okay, so if you take derivative with respect to k, then it will be 2 omega d omega dk, which will be omega 0 square minus a Okay, so before that we need to actually take care of this part, large wavelength. So we need to find omega square at large wavelength. So large wavelength means k small, which will imply cos kxa. So omega square will be omega 0 square into 3 minus so this will be omega 0 square into a square by 2 into k square, where k square is k kx square plus ky square plus kz square. This is omega square. Now if we simply take root over of this will be omega 0 a k by root 2. Just need to find d omega dk. So omega 0 a by root 2. This is the answer. So omega 0 a by root 2. So option D is correct. Okay, so let's move to the next problem.
Sir, once again move on up, sir.
No one? Hello.
Previous problem. 1 second, show me, sir.
Yeah, yeah, yeah. Sure.
Okay, sir.
Here mu and gamma are constant. So the answer is proportional to cos C is again some constant, or option B, answer is proportional to simply electric field. Option C, proportional to, or sorry, independent of electric field. Or rather, we can put this way: e to the power 0.
Sir, position is not visible.
Proportional is not, oh, I'm not writing proportional. So this is proportional symbol. Okay.
Network failure maybe.